in today's video, we'll look at your first, OpenFOAM simulation, lid-driven cavity. Lid-driven cavity is a very fundamental problem in CFD, and anyone who starts their CFD journey starts with this problem. It's a very basic problem. The idea is that we have a simple cavity with the top lid open or moving, or you can imagine a room with no roof and a gust of wind moving horizontally, whatever suits you. The idea is that we look at a very simple problem wherein we can realize a simple flow physics. This problem can be used for writing your own code, which thereafter can be modified for other problems. Due to the simple nature of this problem, usually it is selected for writing your own CFD code. So assuming that you are new to OpenFOAM and you are starting out your OpenFOAM journey, your CFD journey with OpenFOAM, I am preparing this particular video. All right. So we are looking at a simple, as I said, 2D cavity. The other walls are fixed, and we will assume a no slip condition here. All right. And the top lid, as I said, is moving with a constant velocity, say u. As a result, we are going to see some recirculation happening inside, some primary vortices, some secondary vortices, depending on the Reynolds number. We'll see different physics. For now, let us fix the Reynolds number to be 100 so that we can focus on understanding how to run our first OpenFOAM simulation. So as I said, this is the problem definition. And now let us move to the OpenFOAM setup. I'm assuming that you are aware of what is OpenFOAM and you have already installed an OpenFOAM version on your setup. Assuming that you have installed ESI version. The version that I have is 2406. I think it has been recently updated as well. But then again, it doesn't matter because we are looking at a very simple problem. So yes, any OpenFOAM version should be good. Now, let us move directly to the OpenFOAM setup. If you have installed this version of OpenFOAM, its setup should be located in user, lib, and here you have to look for OpenFOAM folder. Depending on the version, you'll have this particular setup right here. OpenFOAM is an open source tool, so the source code is available to you. Here we would want to go to tutorials folder. Look for the closest case and then modify it. Luckily, in our case, a cavity folder is already available. We have to navigate to incompressible flow, icofoam, cavity, and I'll select cavity over here. I'll simply make a copy so that I don't tamper with the original file, which can be used later again. I open the cavity folder. Now let us revisit our problem and see what are the various conditions. We are intending to solve a 2D, all right, incompressible laminar Nothing fancy. For this, we have also created the domain, as I have already told you, a simple 2D domain, a 2D square if you may, with the droplet moving. Alright, what are the other things? I assume that, say, the fluid is air, and what are the governing equations that we are going to solve? Obviously the Navier-Stokes equation, so we'll have the continuity equation and the momentum equation. I am writing in its general notation. That would be easy to understand. So if you observe this equation, alright, if you observe this equation, we've got two fields, more or less, because since we are only focusing on the fluid field for now, we have pressure and we have velocity that we are supposed to solve. Alright, pressure and velocity. Alright, so this is what is there right now in front of us. Let's head back to the case. So here, if you see, a typical OpenFOAM case will have three components: 0, constant, and system. 0, if you open this folder, you'll see there are two files with the name P and U. And C, we are supposed to solve P and U. So what does that mean? It means these are the initial, or this is the initial time step, initial condition, if you may. Let us open them. And if you see carefully, we have the scalar field pressure that's supposed to be solved and the velocity. If you look at the pressure or any typical file, OpenFOAM file, you will realize that it has a common header which makes the formatting easier. Basically the color scheme, so that you can differentiate between the components. The second aspect is all these will have certain declarations, but all these declarations are very user friendly. So let us look at the pressure field. First, we'll declare the dimensions. The dimensions may look a little different to you because this is kinematic pressure, P by rho. It's a wall scalar field that has been mentioned. Internal field represents the values of all the inner cells. Currently, since this is the initial step, we'll assume 0 everywhere. You can also make a better assumption if you have. And these are the boundary conditions. These are the boundaries. Again, we will talk about this a few moments later. Again, if you look U, in U, we have dimensions, meter per second, internal field. Unlike pressure, this is a vector. Hence, we have three different values for X, Y, and Z directions. We'll talk about the boundary condition, how to define them a few moments later. But notice, this is what we want, and it's already in that fashion that the top wall is moving with a certain velocity, horizontal velocity if you may, and we have no slip on the other walls. So this checks, right, that we are solving for these two fields, and the boundary conditions are that here on the walls U is 0, V is 0, and that condition applies on all the walls. And on the top wall we have U is equal to 1, V is equal to 0. Again, the third dimension is obviously going to be 0, needless to say, right? Let us go to now constant folder. What does it have? Transport properties. Beautiful. So transport properties, let us open it and we will see that this file, transport properties, will be used to define the entities that are going to stay constant throughout the simulation. After a while, when we run or when we generate the mesh, you will also see that it will contain a folder, polymesh, which consists of all the files related to mesh. Now, since this is a laminar flow, we are looking at a very simple case. If suppose this was a turbulent case, there would be another file called as turbulent properties. If suppose we have source terms, we would look at files like FE options. Again, if compressible flow or heat transfer, there would be more files. But this is a very simple condition. Hence, we are looking at only one file, transport properties, only one term, kinematic viscosity. From where, if you may ask? From here. Yeah, from here, kinematic viscosity. We need that. So this checks. So we have seen we are solving for, P and U. It is there in the 0 folder. We need to define kinematic viscosity. It is in the constant folder. This checks. Moving on, let us go to the system folder. Lot of files. Let us talk about them one by one. Let us start with control dict. Now, obviously, this is a CFD simulation. So we need a solver. We need a source code. Notice the header is there. Yes. Here we declare which solver we are going to use. The solver is OpenFOAM. OpenFOAM is a very simple, unsteady state, incompressible solver. Yes, we are using that. When do we want to start the simulation? Obviously at the 0 time step. When do we want to end the simulation? You declare the time when you want to end. You can change that. What are your time steps going to be? Or the size of your time step, what is going to be? Based on current number, you can calculate that. You can enter here. When do we want to write the simulation so that you can visualize the progress? Or at the end of the simulation, you can visualize the overall animation of the simulation. How often do you want to write that? Right? And how many files do you want to keep at a given time step? If I write or if I change the value 3 or 5, at any given time, only 3 or 5 time steps are written so that you can save space. Again, write format, write precision, all these things are typically required when you run a CFD simulation. But then again, let's not complicate things. This is our first simulation. This is what we are looking for. Most probably only these lines are important to us right now, so we'll focus on that. These checks. Moving on. What about this file, decompose per dict? What does it do? So decompose per dict is a very beautiful or provides us a very beautiful option of running parallel simulations. At nowadays, laptops usually have around 8 cores, 10 or 12 cores, 16 cores. So you can divide your mesh in these cores and run the simulation parallelly so that you can complete the simulation faster in comparison to running a serial simulation. But again, it's your first simulation, so it will not complicate things. So maybe I remove this for now. Let us focus on these 4 files alone. And these are the most important files for our simulation, first simulation. So we have done control dict. Let us go to FA schemes. Now you see, we here talked about different terms, right? Obviously, you need special treatment to deal with gradients, to deal with Laplacian terms, to deal with divergence terms, and the gradients. So you need different schemes to handle these terms, because any programming language doesn't know how to handle mathematical operators, so you need to define these things. Obviously in OpenFOAM the library already has those definitions, but you'll have to call this. So how do you handle the gradient terms? How do you handle the divergence terms? How do you handle the Laplacian terms? What interpolation scheme are you going to use? What are you going to do about normal gradients? So all these things you can define here. FE schemes. What about FE solution? In FE solution, again, we are solving for pressure and velocity. How are you going to calculate or solve those fields? What is the mathematics behind that? So that has already been defined in the library that you will call here. What algorithm are you going to use for pressure correction? So here we use a piezo algorithm for the unsteady simulation. That we call here. Obviously, these individual terms, what is PCG, what is DIC, what is smooth solver, what is solver, what is sim-Gauss-Seidel, all these things are there in the OpenFOAM library. You will explore them slowly, one by one. Don't overwhelm yourself in the initial simulation itself. Understand what are they and leave it at that. So far, to revise quickly, we know that an OpenFOAM or a typical OpenFOAM setup has 0, constant, and system folders. In 0, we have the fields that we are going to solve, their initial condition. In constant, we have the things that are not going to change throughout the simulation, as the name suggests, constant. So we define the transport properties here, we defined the source terms and all those things that are not going to change throughout the simulation. And then in system, we control the simulation. We decide what schemes are we going to use, what solvers are we going to use, and so on. Other things related to the numerical part. All right. And now the most important part, the mesh. Because at the end of the day, we need to discretize the space. So for space discretization, we are using finite volume method. True. But what is going to be the logic for that? Now there are several different ways to do this. But as a beginner, as a person who is new into this OpenFOAM environment and someone who is working on fundamental problems, they should select BlockMesh Dict or BlockMesh as a mesh generation option. So in BlockMesh Dict, let us open it and let us understand how things works. In BlockMesh Dict, again you will be welcomed by the header. Then we have something called as scale. This is basically scaling up or scaling down your domain. Again, there is no need to overwhelm yourself by this. You can simply keep it 1 if you don't understand what's going on. If you're not sure about whether scaling up or scaling down or how to do it, just keep it 1 for now. Things should work fine. Here we use a bottom-up approach, meaning first we draw the vertices, then we join those vertices into a block, and that is how we define our mesh. Let me help you visualize this. So if you see if you try to understand what these lines mean, it will be very easy for you to visualize what's going on. Let us look at our problem once again. We have a simple cavity. Now you may be surprised that I have drawn a cube, but we kept on saying that we have a 2D problem in hand. Try to understand one thing. OpenFOAM has all the meshes always in 3D. But we convert a 3D case to 2D case by declaring the front and the rear face as empty. This is one option in OpenFOAM by using which you can convert a 3D case to 2D case. I hope that clarifies your doubt if you had that. Now, as I said, the first job is to define all the vertices. We need 8 vertices to define a block for a face, and that is how we are going to build this mesh. So it's a simple cavity case, so I'll simply go for 8 vertices. So this is 0, 0, 0, right? This is the second point, 1, 0, 0. I'm drawing a unit mesh. Not necessary that you always have to draw a unit mesh. I could have written 10, I could have written 100, it's up to me. This is 1, 1, 0, and this is 0, 1, 0. All right, and then I decide that okay, I go by assigning it simply 0.1 as a thickness. Doesn't matter, you can give it anything, because front and rear face we are going to define as empty, so it doesn't matter what thickness you end up giving and what number of divisions you give there. It's simply going to be always 1, doesn't matter. So here I give it 0.1 for now. All right, so accordingly the coordinates of the points on the rear face, all right, will change, in the sense it will become 0, 0, 0.1, 1, 0, 0.1, 1, 1, 0.1, and 0, 1, 0.1. All right, now in OpenFOAM the software automatically numbers itself, or these points, as you define them. So since you defined this point over here as your first point, it will automatically number it as 0. Accordingly, 1, 2, 3, and then 4, 5, 6, and 7. So we've got 8 points. And the numbering always starts from 0. So if you see the sequence that we have defined it here is how it's going to number those points. All right. So once we have defined all the vertices, we can then join them by blocks, as has been mentioned here. Now there is one particular thing to keep in mind over here. The pattern matters. The pattern matters. So in what pattern you select these points matter a lot. So usually what one does is he adopts an anti-clockwise approach. So 0, 1, 2, 3 for the front face. As you can see here, 0, 1, 2, 3. And 4, 5, 6, 7. Right? 4, 5, 6, 7. Anti-clockwise for the rear face as well. So I will have 0, 1, 2, 3, 4, 5, 6, 7. Simpler. All right. Then the boundary. If you want to check whether you have defined everything right without going into this boundary, what you can do is simply delete it. Maybe paste it in another cell. If you are aware with commenting, or if you know C++ a little bit, then you can also comment these lines. And then what you can do is you can go to the main location in the sense where we had the 0 constant and the system not in the system. Don't do this. Go to 0 constant and system and then open a terminal, or open a terminal at that location and run BlockMesh. And also run ParaView. Important note here is that you should have installed ParaView. Mostly when you install OpenFOAM, ParaView software is not installed along with it. So you'll have to install it separately by simply using sudo apt install ParaView, or just go to the ParaView website and install it from there. And then when you run ParaView is loaded. ParaView is a post-processing software. And when you click apply, you should be able to see the mesh that has been generated so far. So we'll go surface with edges. You can see particular this. Okay, so we have not yet talked about that. Let us keep it to that. Now, how many divisions do I want to give in each direction? That you can define it here. X, Y, and Z. Simple grading is basically, if you want to go for a non-uniform mesh, you can change the simple grading option. Where you want a fine mesh, there more cells will be clustered, and where you want coarse mesh, less cells will be clustered, and then the distribution happens very smoothly. You can change the values here. This I will talk in the next video, but for now let us just focus on understanding a typical OpenFOAM case. All right, so ignoring this and focusing only on this, by using this, we define the number of divisions in X, Y, and Z direction. So if you say increase this to say 50, and you go again and run BlockMesh command to take it into effect, as you can see, the number of cells have now changed to 2500. And ParaFoam, to view the mesh, apply, surface with edges, you can see now the number of divisions have been increased. Note that in the Z direction, we don't want any division, so we don't have anything there. And this is what it is. All right. Now, how to define boundaries? How to define boundaries? Now, let us look at this case again. Here. All right. So let me clear it out a bit. Yeah. If you look at it carefully, aside the front and rear face, we have top, we have bottom, we have left, and we have right. 4 boundaries. All right. So how to define these as a boundary in BlockMesh so that we can define boundary conditions there. All right. Now, if you remember, the top wall is moving. This wall is moving. And what are the points related to this wall? 3, 2, 6, and 7. I'll simply use those. So I'll go 3, 7, 6, 2 or 3, 2, 7, 3, 2, 6, 7 in whatever fashion, but they have to be connected, or we have to adopt a certain pattern. So here I define 3, 7, 6, 2. All right, as a moving wall, and I'll define the type as wall, because again, this is a wall that is moving. There are different types of boundary condition. You can also define this as a patch, doesn't matter. However, here the other walls, there we need to define no slip, and no slip has to be defined on a wall. Even you can define it as a patch and then say that velocity is 0 in all the directions, doesn't matter. This is a simple problem. So let us not focus too much on these things and understand how to run the case for now. So moving wall, we create a separate boundary, and since all the rest of the boundaries we need to define the same boundary condition, so we'll club them and merge them together. Simple as that. So I call it as a moving wall, I call it as fixed walls. You can call anything that you want. Here I have defined the front and the rear wall, or the rear face, so that I can define it as empty. If you choose not to define this, OpenFOAM will automatically deem it as empty, and it will be created or treated as a 2D case. So you don't have to worry much about it. But yes, it is always good to define so that we don't make any mistakes. And if you check the numbers, it all adds up. So that is what it is. I hope this particular part is clear, to quickly revise, we have a scaling up or a scaling down option. Then we define all the vertices. By joining those vertices, we create a block, and we have then define the boundary conditions, or we are supposed to define the boundary conditions. In edges, we can define curves, but since there is no curve, so we can leave it to that. And this is a typical OpenFOAM case. How to run your simulation? Very simple. Simply type the solver name and enter. You simply run your simulation, and then you click ParaFoam, or you run ParaFoam, and you can visualize your results. So there is velocity field, there is pressure field. If you look at the velocity field and go to the final time step, or even run the animation, as you can see how the circulation region is appearing over there. You can even plot the streamlines, maybe reduce the resolution a little bit so that it appears clear, and this is what it is. And if you run the simulation, as you can see, the generation of the vortex. Obviously, if you run this longer, you will get to see a steady state, and that's that. You can even notice the secondary vortices forming over here. So this is how you run your first safety simulation. Thank you.